Hello all, good evening. Welcome for the next session on Algebra, sequence and series. Uh, Second part of that. We already had our first session on sequence series last time. So yes, all of us are set to discuss more challenging, exciting questions on sequence and series. Uh, there's a common theme, I would say, to most of the questions that we have today. I'm focusing today on the most recent year questions. Uh, it has been observed that a lot of questions on sequence and series involve a kind of a recurrence relation, a relation which defines how each term depends on some of the previous term, right? So that will be a theme on most of the problems today that we'll be discussing, and how to handle questions regarding the same, and some miscellaneous questions as well on the topic. So ready to start? Let's jump in. Sequence and series, second session. Here we go. First one, what would be the thousandth term of the sequence given below? The sequence is something that can be easily identified, that what is the pattern that we have over here. A very unconventional question, and such kind of uh, relation where we have a certain number repeating a certain number of times, and then it progresses so on and so forward. This kind of sequence questions have been asked on this also quite many times. We have to find the thousandth term of this sequence. 1, 3, 5, 7. So obviously the numbers over here are odd numbers, but it is not just the sequence of 1, 3, 5, 7, 9 and so on. It is the sequence, as you can see, where 1 comes once, 3 comes thrice, 5 comes 5 times, and so on. So the odd number is repeated as many times as is the value of the number itself. Very interesting, right? So how do we figure out that what is the thousandth term of the sequence? Interesting. Let's see. By the way, I'm waiting on my chat box also. If you can crack this, I'd be happy to and glad to see if anybody can get this, right? And we'll announce the name of the person also who gets this. So let me know if you get this or not. Okay, I'm looking out now. Here is what the logic here it is. 1 comes once, 3 comes thrice, 5 comes 5 times. So when we are finished with writing the nth odd number, how many numbers or how many terms we have used? Because we are interested in reaching to the thousandth term, so we should be analyzing that when we have written the nth odd number, the nth odd number is 2n minus 1. For n equal to 1, 2, 3, we get 1, 3, 5, 7 by putting 2n minus 1. As we put n equal to 1, 2, 3, we get 1, 3, 5, 7, right? So when we write the nth odd number, which is 2n minus 1, how many terms have been used? How many terms have been written? That's what we should be thinking about, right? Can I say the number of terms? The number of terms by the time we have finished writing the nth odd number is 1 plus, so for 3 we wrote it thrice, so plus 3. So when we ended writing 3, we had written 1 plus 3 number of terms. When we ended writing all the 5s, how many terms we have written? 1 plus 3 plus 5 and so on. So can I say that it is the sum of this sequence 1 plus 3 plus 5 plus 7 and so on, which is up to 2n minus 1. These many number of terms we have written. This summation we can easily find using the AP formula, right? Applying that gives us n square. It is very well known. All of us should know this. The standard result, the sum of the first n odd natural numbers is n square. You can check that. 1 plus 3 is 4. It's 2 square. 1 plus 3 plus 5 is 4 plus 5, 9. It is 3 square. So that's a pattern. That's a formula. We should all know. Any which way you apply the AP formula summation on this, you get n square. So the number of terms is n squared by the time we have finished writing the nth odd number. For example, let's say I have finished writing all the sevens. How many terms I have written? Put n equal to 4 because 7 is the fourth odd number. So 4 square 16. Indeed, this is the 16th term, isn't it? Okay. So this is the number of terms which is n square, which should reach somewhere near to this mark of 1000, which I want to which up to which I want to reach, right? So n square should reach somewhere in the range of around 1000. So we have to think that which perfect square is nearest to 1000. 30 square is 900. 31 square is 961. 32 square is 1024. So 31 square is 961 implies that the 31st odd number was written for the last time when it was the 961st term, and the 31st odd number is 60. 31 into 2, 62 minus 1, 61. And the 961st term was the last time we wrote 61. Now the subsequent 32 terms from the 962nd term all the way up to 32 square being 1024, the 1024th term, all these terms are going to be 63. And that's my answer. Right? The 32nd odd number, which is 63, is therefore the 1000th term of the sequence. Right? Interesting? All right. Let's see. Next one. Yes, people. The value of this expression. Again, let me give you 1 minute. Let me give you 1 minute to think on this before we start discussing, so that I can get some answers if possible from you. Remember, you don't necessarily have to calculate this exactly because options are in a range. Is it less than 0.25? Is it between 0.25 and 0.5? What's the range of this? All right. Now, so this is a product, right? This is not a summation that we have to do. However, there is a sequence attached to it, and we have to do the product of all the terms of this sequence, where each term is obviously of the form, the nth term is 1 minus 1 by n square, where n starts not from 1 but from 2, right? N starts from 2 and goes up to 30, right? That's the sequence that we can see. So uh, there is something about this expression which would make it get simplified, and we can calculate this quite exactly. See, the thing is, okay, Kashmi, we'll just check now. So Kashmi, if you have done this by a little bit approximation and guesswork, here is something that I would want to discuss. You see, there can be a slight mistake, or there is a slight chance of error if we try to calculate this approximation by approximation, in the sense that, okay, let's calculate the product for the first few terms only. The thing is that there are so many terms. There are 29 terms. Each term is slightly less than 1. So as you are multiplying, the cumulative effect, the compounding effect of the product of all such values which is less than 1, the eventual product might be quite low. So there's a chance of an error. Now this is what we should have done, right? Instead of just calculating the first few terms, which has a chance of error, this is how we should do this. So the nth term, let's simplify that. The nth term, can I say, is n square minus 1 over n square, right? N square minus 1 over n square. We can factorize this as n minus 1 times n plus 1 over n square. N square is nothing but n into n. I deliberately want to write each term in this form and then let's see what happens. Okay, so now I'm actually writing not literally all the 29 terms, but the first few and the last few terms. You will see what happens. So the required product is, so putting n equal to 2 and up to 30 in this expression, and I'm writing the product over here. So n equal to 2, so 1 into 3 over 2 into 2, right? Into, then second, for put n equal to 3, you have then 2 into 4 over 3 into 3, right? Then put n equal to 3, sorry, n equal to 4, you get 3 into 5 over 4 into 4. Just write a few more terms. 4 into 6 over 5 into 5, 5 into 7 over 6 into 6, right? And so on. I think this much is sufficient to understand the pattern. And also, dot, 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 I'm writing from the last. Let's say putting n equal to 26, or let's say putting n equal to 25. We get 24 into 26 over 25 into 25. Then 25 into 27 over 26 into 26. 26 into 28, 27 into 27. 27 into 29, 28 into 28. I think we have two more. 28 into 30 over 29 into 29. And I think last now we have 29 times 31 over finally 30 into 30. Now you see, the point is that the things will start obviously simplifying. See, look at the pattern very carefully. This 2 will cancel with this 2. This 3 will cancel with this 3. This 4 with 4. This 5 with 5. This 6 will also cancel with the subsequent numerator, right? Likewise, this 3 cancels with this 3. This 4 cancels with this 4. 5 with 5. 6 with 6. 7 with the denominator of the subsequent term. So eventually, except for some numbers in the first term, everything starts cancelling off in all the terms. Nice. And likewise, in the last, from the last, again, so looking at this 29, this cancels with this 29, this 30 cancels, sorry, my bad. This 29 cancels with this 29. Just a second. Have I written this correctly? Yeah, just 1 second. Let me start from here. This 26 cancels with this 26. Okay, this 27 with this 27, this 28 with this 28, this 29 with this 29, and this 30 will cancel with this 30, right? So these cancel off. Likewise, likewise, this 25 would have also cancelled in a similar manner with the numerator of the previous term, right? And then this 25 goes with this 25, this 26 with this 26, this 27 with this 27, this 28 with this 28, this 29 with this 29 also goes off, and this 24 likewise would have gone off with the previous denominator. Again, everything cancels off except for some numbers in the last term. So we have 1 by 2 from the first term, and 31 by 30 only remains from the last term. So this is 31 by 60, and 31 by 60 is obviously more than half, slightly more than half. So it's between 0.5 and 0.75, right? So pattern is definitely there. You had to write the algebraic expression of the nth term and then work it around, right? Approximation in this question is prone to error because every number is slightly less than 1. You cannot uh, practically come to the value by judging from the first few terms, right? So as I said, I brought some miscellaneous questions today, the kind of pattern based problems which are expected. All right, now uh, now we're starting with, as I was saying in the beginning, recurrence relation based problems, uh, where a sequence is defined such that a particular term depends on the previous terms, right? So let's understand through this problem. A sequence an, a is the name of the sequence, stands for an stands for the nth term of a sequence. This is the common notation for denoting a sequence is such that an plus 1 equals an minus 1 for n greater than equal to 2. If Sn denotes the sum of its first n terms, if Sn denotes the sum of its first n terms and a1 and a2 are not 0, what is the least value of n for which Sn is 0? So this is the common way the problems are being designed these days, that you have to understand the mathematical wording of the question first of all. Basically, the question is saying each term is the difference of the previous two term. An plus 1 is an minus 1, right? To initialize this sequence, I need the first two terms, right? The first two terms are the starting points, the initial values without which we cannot start getting the values of the terms, right? Once those values are known, then the third term and onwards, right? The each term is the difference of the previous two terms. And we are asked that if the first two terms are non-zero and not equal to each other, then when does the sum of the first n terms become 0 for the first time? Because what is the least value of n, right? Now, we don't know the values of a1 and a2, but all that we know is that they are non-zero. So from a3 and onwards, we'll start defining the terms, right? Let's just, for convenience of writing, let's just write a1 as a number x and a2 as a number y, which are variables, so that we can then start writing the subsequent terms in terms of that. So what does become a3? A3 becomes a2 minus a1, which is simply y minus x. Now, keeping the options in mind, I am expecting the sum of either 4 or 6 or 8 terms to be 0. If none of that happens, so then D might be the correct choice. Let's see what happens. Because there is nothing to do but only to check, right? So we have to start writing the first few terms as per the definition. A1 and A2 are the initialization of the sequence. Once they are known, then each term is known in terms of them, right? So A3 is y minus x, simply A2 minus A1. Likewise, A4, which is going to be equal to A3 minus A2. So y minus x minus y. So y and minus y will cancel, and I'm left with minus x, right? Now, is the sum of these terms 0? Well, let's check. X plus y. So A1 plus A2 plus A3 plus A4. Right, so S4, right? So x plus y, a1 plus a2 plus a3, which is y minus x, plus a4, which is negative x. So x and minus x goes, no, this is not 0, this is 2y minus x, right? This is not 0. So let's continue. Let's find a5. A5 will be a4 minus a3. A4 is minus x, and a3 is y minus x, so negative of that, so minus of y minus x or minus y plus x, so this gives me minus. Perfect, right? This cancels off, and minus y. 5 is not an option, so I'm not checking s5. A6, so a6, a5 minus a4 minus y, and minus a4, which was minus x, so minus of minus x plus x, so minus y plus x. All right. Now my S4 was 2y minus x. So my S6 would be S4 plus the fifth and sixth terms. S4 we had already obtained as 2y minus x. And I'm adding now A5 and A6, which is minus y. So minus 2y and plus x. Right. So this is also minus y basically. Minus y. So yes, this does become 0 indeed. 2y minus y minus x plus x. Yes, this goes to 0. So just what we had to do. We did not know any numerical values, right? But all we had to do was follow the script of the question. Question is saying you should be able to reach to the sum of the first either 4 or 6 or 8 terms to be 0. Just check when does that happen. So all that you had to do was follow this recurrence relation, this relation which defines each term in terms of the previous two terms, and keep on defining these terms subsequently in terms of the first two terms, and just check the condition. That's all, right? So we'll see more on this. Now I'll start discussing some of the previous year questions as well. Let's see the fourth question. All right. Uh, I think something somewhat on the lines of the first question, right? The natural numbers are divided into groups as the first group. So groups are written in this way in the brackets. The first group just consists of the number 1. The second group consists of the numbers that the subsequent 3 natural numbers 2, 3, 4. The third group consists of the subsequent 5 natural numbers 5, 6, 7, 8, 9. So something like that. 1 number, 3 numbers, 5 numbers. So each group consists of an odd number of numbers. What is the sum of the numbers in the 15th group? Right? Well, so I think we have already seen this, that the sum of the first n odd natural numbers is n square, right? So it is not difficult to identify that the first group ends with the number 1, the second group ends with the number 4, the third group ends with the number 9. So it's very clear and it is very obvious, since the sum of the first n odd natural numbers is n square, so the nth group in this case is ending with n square. That is obvious, right? And that is the only thing that you need to catch, and then the answer is a simple cakewalk, right? I have to find the numbers in the 15th group. I'm interested in the last number in the 14th group. I have identified that the nth group ends with the number which is n square, because the sum of the first n odd natural numbers is n square, because the number of numbers till the nth group is nothing but 1 plus 3 plus 5 and so on, right? So the 14th group is going to end with the number which is 14 square, right? 196. Brilliant. Hence I know my 15th group is going to start with the next number, right? That's my start of the 15th group. And when does it end? What is the last number of the 15th group? 15 square, 225. Done. I just need to add the numbers from 197 all the way up to 225. That's all. So that's it. S15, the sum of the 15th numbers in the 15th group, is therefore simply the sum of these consecutive natural numbers 197, 198, 199 all the way up to 225, right? So this is the sum of an AP. Sum of an AP is number of terms up by 2 into first term plus last term. How many numbers these are? 225 minus 120 minus 197, which is 28 plus 129. These are 29 numbers. So 29 by 2, number of terms by 2, times first term plus last term, 225 plus 197, 422. 422. Right, so 29 into 211. The last digit of the product should be 9. That must be the answer, 6119. Right, 9 into 1, 9. Only one option has the last digit 9. Right, you can obviously you can multiply this, you'll get this 211 into 29, 6119. Right. Yes. So as you can see, this kind of patterns are very frequently seen in problems, right? Okay, let's see next one, people. Now I'll give you 1 minute to just digest this problem. Let me pause for a minute. I would want you to read this, understand this, and try this for a minute. Then I'll discuss. All right, now, so you see what this question is telling us. For a sequence of real numbers x1 up x2 and xn up to, now this equation is alternate sum and difference of the terms. So this, the trick is that here we don't have an expression for the it's not a simple summation of the terms. It is x1 minus x2 plus x3 minus x4 and so on till nth such value, and that equation for that is given as n square plus 2n. Well, as you saw in the last to last problem, that when we are given such kind of a relation, whether it's a recurrence relation or an equation in this form, all that we need to do is just start using that equation or that relation for n equal to 1, 2, 3, and so on, so that we can identify what are the terms. That's the only thing and the obvious thing that has to be done, right? And this is an exact formula in terms of n. It is n squared plus 2n, right? Or which can also be written as n into n plus 2, right? I want to write it in a factorized form, right? So just putting n equal to 1 in this equation, because this equation is valid for all natural numbers. So even for n equal to 1, this should work. So for n equal to 1, it will simply give me the first term, x1 equal to, put n equal to 1, 1 into 3, 3. That's it. So first term is 3. Done, right? There's no other data. You only have this equation, and it is true for all natural numbers n. So it works for everything, right? The first term is 3. Uh, we'll worry about this later on. Let's first of all identify the pattern in the terms, right? For n equal to 2, what do we get? We get x1 minus x2 is equal to 2 into 4, 6. So what does this tell us? Sorry, 2 into 4, my bad, 8. Right. Now, what is x2 therefore? X2 is therefore x1 minus 8. X1 was 3. So 3 minus 8, which is minus 5. Let's start getting some terms until we understand the pattern. For n equal to 3. For n equal to 3, so x1 minus x2 plus x3. X1 minus x2 already we have understood is nothing but 8 from above. And that plus x3. So putting n equal to 3 in this, 3 into 5, 15. 8 plus x3 is 15. X3 is 15 minus 8, 7. 3 minus 5, 7. Odd numbers we're getting. Let's just confirm what's the pattern with one more recurrence. Let's put it one more time. So x1 minus x2 plus x3 minus x4. And this much from the above was 15. So this is therefore 15 minus x4. And that equals, putting n equal to 4 here. So 4 into 6, 24, which means that x4 is coming to be 15 minus 24, which is minus 9. Now the pattern is definitely clear. It is the odd numbers starting from 3, not starting from 1, starting from 3, and alternate plus minus sign is there, right? 3 minus 5, 7, minus 9. You can check. You can definitely go for the next one. You'll get the next term as 11, and the next term as minus 13, and so on. So what is our job? Our job is to find the sum of the 49th and 50th term. Now, don't jump on to calculate the 49th and 50th term. Understand the pattern in the sum of two consecutive terms. What is x1 plus x2? What is x1 plus x2? 3 plus minus 5 minus 2. What is x2 plus x3? Minus 5 plus 7, which is 2. Minus 5 plus 7, which is 2. What is x3 plus x4? 7 plus minus 9, which is minus 2. We all know that x5 will be 11. So next, x4 plus x5 will work out to be minus 9 plus 11, which is 2. So what is happening? The sum of two consecutive terms is alternatively minus 2 and plus 2. And when is it 2 when is it minus 2? It is minus 2 when the first term is either x1 or x3 or x5, the odd value. And here also we have this as odd. So when it is odd, we are getting this as always minus 2. So minus 2 is the required value. X1 plus x2, x3 plus x4, dot dot dot, x49 plus x50 works out to be minus 2. Right? Pattern identification using the recurrence relation put n equal to 1, 2, 3, get the values of the terms, get the job done. All right, interesting. Another one uh, on a similar kind of a pattern. If x not equal to 1, x1 equal to 2, and xn plus 2 equals 1 plus xn plus 1 over xn, n is 0, 1, 2, 3, and so on, then you have to find the value of x 2021. All right, let's see. So just we need the values of the, we know the values of the first two terms. So each term from the, for n equal to uh, so this relation is true for all values of 0 and 1 and so when you put n equal to 0, you get x2 and so on. So from the, actually the third term, which is x2 and so on, we have this relation. X0 is 1 and x1 is 2. These are the initial two terms given to us, right? And then this relation should help us to identify the values of the subsequent terms. So what is x2? 1 plus x1 over x0. So 1 plus x1, which is 2, over x0, which is 1. So this is 3, right? Okay. Only job is to put the values of n, get the values of the terms. X3 is 1 plus x2, which is 1 plus 3 over x, 1 plus x2, 1 plus 3 over x1, which is 2. So 4 upon 2, which is 2. 1, 2, 3, 2. Till now it looks like random, but let's see what happens. X4 is 1 plus x3, which is 1 plus 2 over 3, which is well 1. Okay, 1, 2, 3, 2, 1. 1, 2, 3, 2, 1. Right, increase these 2, 3 back to 1. Okay, let's see what happens now. X5, 1 plus x4, so 1 plus 1 over x3, so 2 is back to 1 again. Again 1. Okay, keep on doing this until you understand a pattern. X6 is 1 plus x5, 1 plus 1 over 1 is 2. X7 is 1 plus x6, 1 plus 2 over x5 is 1 is 3. I think things have started to repeat now. So 1, 2, 3, 2, 1, 1, 2, 3. 1, 2, 3, 2, 1, 1, 2, 3. Again, I'm expecting to get 2. And yes, indeed, 1 plus 3 by 2. Yes, 2. So what's happening? 1, 2, 3, 2, 1. Here was the breaking point. 1, 2, 3, 2, 1. And again, 1, 2, 3, 2, 1. And again, 1, 2, 3, 2, 1, and so on. I got the pattern. It's repeating in a loop, right? There is no new terms except for these 5 terms in a loop over and over and over again. So x0 is 1, x1 is 2, x2 is 3, x3 is 2, x4 is 1, and again x5 is 1, x6, x7, x8, x9, x10, x11, x12, x13, and so on. So what I'm trying to show you is that if the term is a multiple of 5, then your term is 1. If your term is a multiple of 5 plus 1, then your term is 2, right? 0, 5, 10 multiples of 5, 1, 6, 11, and so on, multiples of 5 plus 1, 2, 7, 12, and so on, multiples of 5 plus 2, right? Multiples of 5 plus 3, multiples of 5 plus 4, right? So you have to identify that your number of term gives what remainder when divided by 5. 2021 is a multiple of 5 plus 1, so therefore it should be this term, which is 2, right? X 2021 is 2. So it keeps on repeating, and hence whatever term it was, even if it has asked me the value of the 9999 term, I don't need to manually search for that, right? I don't need a formula over here. It's a recurring pattern of terms in a loop over and over again. So trust your question that just get the first few terms, understand the pattern, and you'll get it. All right, so if this was fun, the next question is going to be very interesting. Uh, Let's take the last question for today's session. This came in CAT 2023 and it was quite an offbeat question, I would say. And I've taken this deliberately because a lot of people struggle with this question. But actually, it's a very beautiful question. Let's see. A lab experiment measures the number of organisms at 8 a.m. every day. Wonderful. Starting with 2 organisms on the first day, the number of organisms on any day is equal to 3 more than twice the number on the previous day. So he does give us a recurrence relation in a word problem manner. So if I want to write this in a form of an equation, what should I say? If the terms are A1, A2, A3, I know A1 is 2, the first term is 2, the number of organisms on the first day is 2. Starting with 2 organisms on the first day, the number of organisms on any day, so let's say AN, or let's call that AN plus 1 on the next day, from the nth day and next onwards, is equal to 3 more than, so this is 3 plus twice the number on the previous day. So AN plus 1 should be 3 plus twice of AN. This is the recurrence relation that we have. So this relation only depends on the previous term, and hence it is sufficient for us to be able to write all the terms. Now the question is, however, not something like a cakewalk this time, because he's asking us if the number of organisms on the nth day exceeds not a very mild value, but a staggering value of 1 million. A million is 10 lakhs, 1 followed by 6 zeros. And you're just starting with 2 organisms the first day. So obviously it's a huge value to reach up to. And we cannot obviously manually start writing the terms and just check that when does it cross that staggering value of 1 million. We have to find the number of, we have to find that day, the lowest possible value of n, means on which day do the organisms cross a million. Well, here is what needs to be done. We do need to write the first few terms. We do need to understand the pattern. Let's do that, right? But we'll not do this manually, obviously, but through some kind of a equation and formula only. What is going to be A2? 3 plus twice of 2. So 3 plus 4, 7. Just write number, right? A3, 3 plus twice of 7, 14. 14 plus 3, 17. A4, 3 plus twice of 17, 34 plus 3, 37. A5, 3 plus twice of 37, 74. 74 plus 3, 77. You can see a pattern has started to emerge. The last digit is always 7. Something is there. Some pattern is there to be understood. Let's write first few more terms. A6, 77 into 2 will be 154 plus 3, 154 plus 3, 157. One more term I'm writing, A7, 157 into 2 will be 314. So 317. Now, what is happening? From the first term to the second term, you added a 5. 2 plus 5 is 7. I'm looking at the successive difference of the terms. 7 and then you added a 10 to reach 17. 17 and then you added a 20 to reach 37. 37 and plus 40. This is a geometric progression. The difference of terms has come out to be a GP, right? Plus 80, plus 160, right? No mistakes. That is happening. So I think I can write an expression over here, a formula, an equation for the nth term in terms of a summation of a GP, right? So I'm just writing this because I know to reach till the nth term somewhere, I have to, from 2, we have to then add plus 5, plus 10, and this is a GP. So nth term, I'm trying to write a formula. Just follow me on this. 2 plus, so 2 was the initial term, and then the GP starts. So in bracket, 5 plus, I'm deliberately writing it in the GP form, which is 5 into 2. 5 into 4, I'm writing it deliberately in the form of GP 2 square. So 5 into a power of 2 basically. For the nth term, I have to understand 5 into 2 power what in terms of n. Now let's understand this. If let's say I had to add till the third term, if I had to reach till the third term, so 2 plus 5 plus 10, for the third term I have to do 5 into 2 power 1. Third term it was 2 power 1. Fourth term it was 5 into 4, 5 into 2 square. So the power over here is 2 less than the number of term. Once again I'm repeating this. This is important to understand. If I'm adding, let's say till the fifth term, so I have to add till what? 5, 10, 20, and then 40. 40 is 5 into 8, 5 into 2 cube, and this is the fifth term. For the fifth term, 5 into 2 cube, so 2 less than the number of terms. So this last thing should be 2 power n minus 2 bracket closed, and I know how to add this. So I've got a formula for the nth term, which I can first simplify, and then I have to check on this, right? So let's simplify this. We all know the formula for the summation of a GP, a standard result. So 2 plus 5, let me take 5 common, and then we have 1 plus 2 square up to 2 power n minus 2 bracket closed. All of us know that the sum of the first n powers of 2 is 1 less than the next power of 2, right? 1 plus 2 is 3, it is 2 square minus 1. 1 plus 2 plus 4 is 7, it is 8 minus 1. 1 plus 2 plus 4 plus 8 is 15, it is the next power of 2, 16 minus 1, right? So therefore this becomes 2 plus 5 whole thing down. This is 2 power the next power of 2. This is till n minus 2, so 2 power n minus 1, the next power of 2 minus 1, right? This is the standard result. You can apply the usual regular summation of GP formula, you get this. So this needs to exceed a million. 10 power 6, 1 followed by 6 zeros, 1 2 3 4 5 6, right? So let's finish this off. Obviously the we have to now just check when does this cross a million. That's all. So it's very difficult to algebraically solve this exactly. Like if I take 2 on that side, it becomes 999,998. So you know that this 2 is very insignificant compared to this whole expression. So nearly enough, 5 times 2 power n minus 1, and even this minus 1 is very insignificant compared to that. So almost you can say your 5 times 2 power n minus 1 needs to cross a million. 1 followed by 6 zeros. So which means that your 2 power n minus 1 needs to cross over 200,000. Now what power of 2 brings you close to this? Sorry, not, yeah, 2 lakhs, right? This was 10 lakhs, this is 2 lakhs. Well, at least we know 2 power 10 is 1024, near enough to 1000. And this is 200,000. So think of this, that okay, 2 by 10 is 1000, nearly 1000. So we have to further multiply with the power of 2 to get to a value of 200, right? 2 by 10,000 into some power of 2 is nearly 200. So 2 power 8 is 256. That would work. So 2 power 18, which is 1024, almost nearly 1000, and nearly 250 is nearly your 250,000. It has crossed the mark. Obviously for 2 power 7, which is 128, 128 into 1024 would be obviously much less than this mark. And therefore you can understand the insignificance of these small numbers like 2 and this minus 1. They don't really matter. So obviously your 2 power n minus 1, n minus 1 needs to be 18. So n needs to be 19. That is when it would cross a million, right? Obviously you can now understand, could not have been done manually. This had to be identified. All right. So this was a fun-filled session. I hope enlightening, enriching us with the kind of things that have been asked and can be asked, right? So stay connected, stay in touch. Let me know uh, what how you found this session, and any queries, any doubts, do let me know. A very important announcement for everyone is the race to 99 that is upcoming on 2nd and 3rd of August. 2 days workshop with all our mentors, uh, GP, Shivku, Jijo, Rahul, GB sir, everybody. So this is the schedule that you can see over here. Smart test taking strategies, VRC cracker, Quant cracker, DLR cracker, way forward. Don't miss it. Something that you should look up to for your preparation. Thank you, Kashvi. Thank you, everyone. I hope to see you very soon with our next session, Algebra. We are not yet finished. We have few more sessions. So I'll see you soon. Thank you so much for joining in. Stay in touch. Uh, we'll meet you quite soon. Thank you. Thank you all. Thank you.